reactions of alkyne. Hopefully we can finish the chapter for alkyne today. And the midterm result will be announced probably today, or before at least the claim plan for tomorrow. And this is again the claim period. Just a confirmed schedule, so you guys can visit here 4 or 9 tomorrow or the day after tomorrow. There are two options you can take. Okay. So again, students whose ID ends with odd numbers can come visit here 5 to 6 p.m. tomorrow or the day after tomorrow. And students whose ID ends with even number, they can come visit here from 6 to 7 p.m. tomorrow and 5 to 6 p.m. The day after tomorrow. 그래서 요 플랜 그대로 저희가 가져가고요. 요 409호로 오시면 됩니다. 그럼 TA 3명이 기다리고 있을 거예요. 그래서 채점 잘 됐는지 오늘까지 가능하면 업로드하고 내일 적어도 클레임 전에는 업로드가 다 완료될 거예요. 그래서 점수를 확인하시고 웬만하면 바쁜 스케줄 없으시면 와서 채점 잘 됐는지 TA들이 좀 더블 체크하고 꼼꼼히 보고 있어서 아마 큰 실수는 없을 텐데 그래도 혹시 모르니 와서 한번 클레임 해보고 싶은 학생들 다들 참여해 주시기 바랍니다. 그래서 홀수, 짝수, 자기 아이디 끝번호가 홀수냐 짝수냐에 따라서 여기 안내된 시간에 맞춰서 오시면 되고 나는 두 옵션 다 안 된다 그러면은 TA나 저에게 이메일을 주세요. 그러면은 TA와 약속을 해서 클레임에 참여할 수 있게 드릴 테니까 웬만하면 이 시간을 준수해주면은 TA들이 조금 수월할 수 있겠죠. 그래서 웬만하면 다들 오세요. 와서 클레임 참여하시기 바랍니다. Okay? So that is about the claim midterm. And then let's continue. To learn about the reactions of the alkyne. Okay. Last time on Monday, we learned about the reaction of the alkyne, starting with the addition reaction of the HX, HBr in this reaction in particular. We learned about the reaction mechanism, and we learned about the rationale why you are getting the geminal dihalide in this case. Right? So after first addition, you will get the binyl bromide, and second addition will give you the geminal type products. Geminal means you have two halo groups on same carbon. Right? So we define the terminology: geminal versus bisinol. Right? And in this case, it's a bisinol dibromide. Sorry, geminal dibromide, meaning two bromo groups on the same carbon. And in this case, right, you have two possibilities, two options, because this alkyne is asymmetric, right? Unsymmetric one in the word. It's an unsymmetric one to an alkyne. So there's an option for the bromo group attached to this carbon or this carbon. And this is a symmetrical internal alkyne case. In this case, this is symmetrical, right? Doesn't matter, right, which carbon the bromo group attachment will give you the same result. That's why you're getting the single product, the geminal dibromide. And we also learned about the addition of the X2 type substrate. In this case, Cl2 and Br2. In this case, you are getting the tetra chloro or bromo products. Right? And reaction mechanism was exactly same, basically same as the addition of Cl2 and Br2 to double bond, the alkene, right? Basically, two equivalent addition is taking place sequentially. Right? So after first addition, and then you can imagine like cyclic intermediate will be formed, right, in the first step, first addition. That's why you're getting the N-type product. And then the same sequence will take place. The second addition will give you eventually the tetrachloral products, right? And then the same thing, exactly the same thing can take place. You're adding Br2. Okay? The second addition will give you the tetra substituted product in this case. And then you can also think about the addition of water, right? Addition of water to alkyne. And you already know the addition of water to alkene, right? The double bond, which will give you the alcohol, right? And in the presence of acid, right, the proton addition will take place. And after formation of the carbocation, right, in this case, perhaps here, right, secondary carbocation is preferable, right, than the formation of the primary carbocation. So after formation of the secondary carbocation, you can attack water, right, and deprotonation will give you the corresponding product, in this case, secondary alcohol. Okay? And basically, very similar thing can take place when addition of water take place to an alkyne, right? And this is a result, right? If this is particularly the terminal alkyne case, right? And again, in alkyne triple bond, right? There's an electron, right, localized to this triple bond. This is a good nucleophile. In other words, the electrophile will add to this triple bonds. And in this case, the electrophile adds to this carbon, right? And this will, and following, right, basically the same mechanism as we discussed for the alkene, you can expect to get this NO type of product, right? The only difference is right here, you have a double bond here instead of single bond. Right? And in this particular form, we call out as a NO. You have alkene and alcohol, the same carbon. So we call out this NO, okay? But we'll discuss a little bit more detail about this in the next slide or a few slides later. But this NO can tautomerize, right, to become the keto form or ketone in this case. So if you take a look at, right, this yellow box, the yellow highlighted area, you can see the difference, right? And this illustrates, right, the tautomerization process. So ketone right here and NO form, right, they differ only in the location of double bond and hydrogen, right? So double bond for NO form exists in between two carbons, right? That's why you put in the first place, right? But in the keto form, you have double bond in between carbon and oxygen, right? And also, if you think about the location of hydrogen, right? In NO form, you have hydrogen attached to oxygen, right? That's why you have the alcohol, right, in the first place. But in this case, you have the hydrogen, right, on this carbon. Right? So again, ketone and NO in this tautomerization format, they form in the location of double bond and hydrogen. Okay? And we'll learn about the mechanism for this tautomerization in the next slide. But before maybe jumping into the detail about tautomerization, you can take a look at this different example, right? Basically the same reaction, same addition. The addition of water to the triple bond, the alkyne, but in this case, the internal alkyne, right? The above one is the symmetrical case, the bottom one is the unsymmetrical case, right? Compared to the previous one, you are running the reaction with the atomic alkyne, meaning you have, right, the carbon with hydrogen, right? In this case, you are getting the enol and corresponding, right, tautomerized product ketone. Same mechanism will take place. You get in this case, right, the one single product. So the keto form, this is a symmetrical case, right? But in an unsymmetrical case, you can expect to have two different ketones, right? Because there are two different possibilities, right? Formulating this enol, and tautomerization will give you this product, right? Or you can imagine, right, enol formation in this on this carbon, and tautomerization of these foam will give you right the second ketone products, right? So that's why you're getting two different products in this case. But in again the above case, right? It's a symmetrical case. Doesn't matter, right? It's the same enol, right? So that's why you're getting only one single ketone. So we'll discuss this later. Compared to this enol versus ketoform, right? Their stability-wise, the ketoform is more preferable, right? That's why you're getting the major product is a ketoform. And this is the keto-enol interconversion, or tautomerization. In other words, that's the terminology, right? Indicates the interconversion between these two forms, right? And again, you have enol, right? On the left hand side, you have arginine, right? And N-E-N, right? Here stands for the arginine, right? And you have the alcohol, right? That's why you call out this enol in the first place. And after tautomerization or keto-enol interconversion, right? This can convert into this ketoform or keto-tautomer, in other words. And again, ketone and enol differ only in the location of double bond and hydrogen. And this is a mechanism for tautomerization. Tautomerization can be catalyzed by acid or base. So in this slide, we are considering the acid catalyzed case. Right? So you have enol again here. If acid around, the hydrogen cation, for example, H3O plus, right? Then following the arrow, you can rationalize how, right, this protonated ketoform is formulated, right? So you can follow the movement of the electron, right? And as a result, you get water from the hydrogen cation, right? And then for the second step, this water will deprotonate the protonated ketone, right? Following this. And this will eventually give you the ketone form, right? So enol can convert into ketone, and this is all reversible process, right? So you can think about the backward process, right? And that backward process will give you, right, enol from ketone. So you should be able to draw, right, the mechanism for the simple conversion. And this is again the acid catalyzed version. And there's a base catalyzed version as well, based in the presence of a base. And in particular, in this example, the hydroxide anion. This hydroxide anion can deprotonate the alcohol in enol, and following the movement of the electron, right, following the arrow, you can rationalize how these intermediates form, right, after the first deprotonation step. Simply, right, the deprotonated form of the enol, right, and then movement of the electron, right, will give you the final ketone form, right? And in this way, right, you are getting the proton, right, from water, and as a result, you are getting the hydroxide anion as a byproduct, and this can go into the first step again. Right? That's why this can be a base catalyzed reaction. Catalyst doesn't consume, but still can promote the reaction. Right? And if you go back to the acid catalyzed version, right, as a result of the second step, you are regenerating the hydrogen cation H3O plus. This can get back to the first step and catalyze reaction without its consumption in net. Okay, that's why this is a catalyzed reaction. Okay, that is the enol ketone tautomerization. You know how this process can take place, right? And you can draw the mechanism for that. But as we saw, right, in different example, terminal alkyne and internal alkyne, they can all participate in the addition reaction, right? Addition of water. But if you can compare, right, the reactivity, the terminal alkyne, generally speaking, is less reactive than internal alkyne. If you think about electron richness and this triple bond, right? You have more R groups around, probably you'll get more electron densities, and that will increase the nucleophilicity of these triple bonds, right? So you can compare, right, ternary alkyne versus ternary alkyne in that way. And also, if you think about the stability of the product, right? Stability of alkene, if you have more R groups around, you can expect to have, right, the higher stabilities, right? So they can lead to the stability of the transition state as well, right? So, anyhow, generally speaking, right, ternary alkyne is less reactive. In other words, internal alkyne is more reactive, right, than ternary alkyne. So, if you want to run, right, this addition type reaction, you need someone, some species or catalyst, right, or promoter, right, and mercury ion catalyst or promoters will be used for the addition of water to ternary alkyne. Okay. 그래서 뭐 잠깐 정리하면 이제 사실 알카인 어디션 타입 리액션, 알켄 어디션 타입 리액션에서 많이 벗어나지 않습니다. 되게 비슷해요. 약간 5번보다 본드가 하나 더 있기 때문에 원래는 싱글 본드가 돼야 될 자리에 더블 본드가 있다. 그거를 이제 알고 계시면 될 것이고, 알켄의 리액티비티를 제대로 알고 계시면 알카인 리액티비티는 그냥 아주 복잡하지 않게 이해하실 수가 있을 겁니다. 지금 알카인의 경우에 이제 물이 들어가는 경우, 알켄에서 물이 들어가는 반응 저희가 이미 다 다뤘어요, 그죠? 알코올이 되는데 알카인은 이제 본드가 하나 더 있으니까 N올이 생기는 거죠, 그죠? 근데 특이하게도 이제 N올이 키톤으로 이제 인터컨버전이 되니까 N올이 생기는 게 아니라 키톤이 생기는구나, 토토머라이제이션을 통해서. 그거까지만 기억하시면 되겠죠. 그럼 이제 알카인이 어디션 반응에 참여하는데, 이제 터미널 알카인과 인터널 알카인을 또 저희가 비교해 볼 수가 있겠죠. 인터널 알카인이 일반적으로 반응성이 높다. 다른 말로 터미널 알카인이 일반적으로 반응성이 떨어집니다. 설명드린 이유에 의해서. 터미널 알카인을 반응을 만약에 보내고 싶다, 그러면 이제 반응을 조금 촉진시키게 할 스피시스가 필요하겠죠. 촉매가 되고 프로모터가 되고 머큐리 아이언이 그 프로모터로 쓸 수 있다라는 이야기입니다. 터미널 알카인에 뭔가 물을 집어넣고 싶다, 그런데 촉매 없이 제한을 하게 되면 반응이 잘 안 가게 되겠죠. Alright, so this is the mechanism for catalysis by the mercury ion, mercury 2+, right? As I mentioned, the terminal alkyne is reactivity towards the water addition is not good. It's not good enough, right? So you need a promoter, or you need a catalyst, right? In this case, Hg2+, the mercury 2+ ion, serving as a catalyst or promoters or activator, right? So what you can see for the first step in this reaction scheme is sort of like activation process of the alkyne. Mercury 2+ ion can interact with the alkyne, right, in this fashion, right, following the movement of electron. You can rationalize this cyclic type, right, cation is formed. Right? This looks pretty similar, right? We discussed about in alkene chapter cyclic, right, bromonium cation formation, right, and for the addition of, right, the halide into the alkyne, right, perhaps the cycling intermediate will be formed as well, right? And after formulation of the cycling intermediate, right, the nucleophile will attack the electrophilic carbon, and in this case, the nucleophile has a two choice, right, to attack this carbon versus this carbon. But we know already that the nucleophile tends to attack more substrate carbon, right? You may recall the transition state argument we made, right? Or rationalizing this reduced selectivities, right? And after attack, right, you can rationalize this ring open intermediate and deprotonation, right, will give you this sort of like the NO fold, right? But in this case, still there's a bonding character in between this carbon and this mercury cation. That's what we call out this is mercury null, right? You have NO structure in this intermediate, right? And applying the mechanism is a study, right? The tautomerization process can give you this mercury ketone down side, right? Now the movement of the electron, right? And removal of the mercury cation, right? And protonation process will give you actually this the free enol, right? Without the mercury ion, and tautomerization eventually give you the final product ketone. Right? So this is how basically the mercury ion, right, involved in the reaction mechanism, activating alkyne and increasing the reactivities and proceed, right, make this reaction can take place. Okay. Right, that was about the addition of water to alkyne, and this is new reaction, the different reaction. But you already learned about this, right? For the alkene, alkene can undergo hydroboration and oxidation, right? That will give you the alcohol products. And this reaction can take place alkyne as well, right? So you can use, right, this boronic substrate R2BH, right? Meaning this boronic center has two R groups, the alkyl groups, right? As we discussed, where the hydroboration reaction of alkene. Right? One of the differences for using a triple bond instead of double bond, right? So after hydroboration, then you can expect, right, these boron substitute alkene will be given as a product, right, following the same reaction mechanism. And then oxidation process, right? The second step will give you enol, right? So you probably recall, right, if you're running, right, the same reaction with alkene, then you are getting the single bond in between this carbon, right? And oxidation, the second step, will give you this alcohol. That was the hydroboration of alkene. But since you're running the reaction with the triple bonds, you are just increase one more bond between these two carbons. Right? And then after, right, two-step, you are getting this enol, but this will participate in tautomerization. So eventually will give you a ketone. Right? So hydroboration followed by oxidation will give you a ketone in alkyne case. The same type of product, right? When you add water to alkyne, right? But mechanism is different, and the product selectivity will be different. Right? And here is a general result from your alkyne when this participates in hydroboration and oxidation. This will give you aldehyde, right? But if inter-alkyne participate in this reaction, then this will give you the ketone. You can expect that, right? Because you can take an example here. If you're running the reaction, the hydroboration and oxidation using this terminal alkyne, right? Then first step, the hydroboration will give you this boron added product, right? And oxidation will simply replace basically, right, this boronic groups to alcohol to give you this enol product, and tautomerization will give you this aldehyde as a product. But in terms of alkyne, you have R group instead here, right? That's why you're getting the ketone. 그려보시면 바로 이해가 되실 겁니다. 그래서 메커니즘 알켄에서 다 배웠던 메커니즘이긴 한데 알카인에 동일하게 적용된다라고 생각하시고 메커니즘을 아시고 시퀀스를 아시면 프로덕트를 이제 설명하실 수가 있겠죠. 이제 알카인에서는 N올이 형성되는 경우에 토토머라이제이션을 더해진다. 그게 알켄과의 차이다. 그거를 이제 구별해서 기억하시면 되겠죠. Okay, this is what you already know. The BH3 with the electrophile, you have, right, the empty petals. It is willing to accept the electron, and this is a special form of the boronic species, right? It can participate in well, right? Addition type reaction, addition to the olefin double bond or even triple bonds, right? And as we discussed in the arcane chapter, right? If you don't have this Berkey or these Berkey R groups, then hydroboration can take place multiple times, right? To give you a mixture of the product that is not what you want, right? You want to make your reaction more selective, right? To get a single product in most cases, right? So that's why you need to use this reagent 9BDN. This is what we already studied in arcane chapter, right? And simply, this can be written as R2PH. The R stands for right, the R group here and there. Right? So hydroboration can take place one more time if stereoprosion is insufficient. Right? But if you have right the R groups right on arcane here and there, then stereoprosion probably be enough. So single addition will take place. So R2BH can be used with R-argine, generally speaking, but R2BH should be used with terminal argine, right? Because terminal argine has less steric hindrance. So if you are not using the Berkey R2BH reagent, then your triple addition probably will take place and you'll get the mixture, right? Which is not what you want. Right, so this is again the hydroboration and oxidation scheme. Okay, so you are running the reaction with right, the terminal argine. Right? You have CH bond, right? And if you're running hydroboration followed by oxidation, right, then this will give you this enol. Right? So you can expect right, this bore added product, right? Added arcane followed by the oxidation reaction will give you this enol form, right? And this enol can tautomerize to become the aldehyde, right? Aldehyde meaning you have COH right? Functionalities. Okay, but if you're running the reaction with right? In the presence of the mercury catalyst, right? Mercury cation, and if you're running the addition of water, right? The acid catalyzed water addition reaction, then in this case, right, you will get this enol, right? And then after tautomerization, you will get the ketone right? Instead of aldehyde. So depending upon the region or reaction condition that you apply, right? You are getting two different products. 그래서 사실 새로운 게 아닙니다. 알켄 챕터에서도 다 다뤘던 셀렉티비티 차이였어요. 그죠? 알켄에서도 1번 위의 조건으로 걸면 그죠? 하이드로보레이션으로 반응을 보내면 less substitute 카본 쪽으로 Br2가 들어가고 옥시데이션 시키면 OH가 말단 카본 쪽으로 들어갔었죠. 알켄에서 근데 물을 집어넣는다. 카보캐라이온이 2차 카보캐라이온이 생기는 쪽이 유리하니까 프로톤 어디션이 먼저 말단 카본 쪽으로 들어가고 세컨더리 카보캐라이온이 생기면 더 차수가 높은 알코올이 생기게 결국 프로덕트가 생겼었던 건데 똑같이 알카인에 적용되는 건데 이제 알카인에서는 알코올이 아니라 에놀이 생기는 거잖아요, 그죠? 더블 번드가 남아 있으니까 에놀 이후에 이제 토토머라이제이션 되는 프로덕트만 상상을 한 단계만 더 더하시면 어떤 셀렉티비티 차이를 더하실 수가 있겠죠. Alright, that was the addition of water and addition of the Br2, right, followed by oxidation, which will be the same in all. Right? Not necessarily same in all, but the same type of product. Right? In all, and participate in tautomerization. Sometimes the enol will give you the aldehyde. Sometimes the enol will give you the ketone. Right? And the next reaction is what we already learned, right, in arcane as well. It's addition of hydrogen to alkyne. And you know the addition of hydrogen to alkene already, right? And this is what you already learned in the previous chapter. If you're on this catalytic hydrogenation reaction of the alkene, right, then this double bond will get saturated, right? Saturated with hydrogen, and then you're getting this the alkane as a product. But if you're running the same reaction starting from alkyne, then you can expect you'll get first the alkene product, right? And sequentially, this alkene will participate in the second addition, right? Which will give you the alkene stage. Right? And mechanism is basically the same, right? Alkyne will approach to the surface of the palladium, right? Nanoparticle or platinum heterogeneous, right? Catalyst. And hydrogen will approach, right, to the surface as well, and syn type addition will take place. But sometimes, right, you want to stop the reaction at alkane, right, stage, right? You want to make again your reaction be selective, right? You want to add just one equivalent of hydrogen, right? And that's what people think about in the past and develop a new catalytic condition or new form of the catalyst, right? And this is the name of the catalyst, right? Very typical one, and there are varieties of the agreed version. But essential idea is the same. Right? This is called the Lindelar catalyst, and if you're using this Lindelar catalyst, then you can stop the reaction at the alkene stage, and alkene, right? Doesn't go forward to your alkene, right? So you can basically stop the reaction at the alkene stage. So you're getting the alkene product, right? The double bond olefin product exclusively. And this is the basics of Lindelar catalyst, where you are still using the heterogeneous catalyst, the palladium surface or platinum surface. But basically you are poisoning the surface. You are poisoning the activities of the catalyst so that alkene cannot undergo the second hydrogenation reactions. And for effective poisoning, you need to introduce this additive, the lead acetate, or lead ion in other words, and then quinoline, this organic molecule. Right? They will occupy the surface of the palladium, or platinum, so that they will effectively deactivate surface to some degree, right? And this deactivated sort of like poison surface will selectively make the reaction, right, for this first addition of hydrogen to alkyne. Right? So that's the basic idea. You are basically deactivating or poisoning the surface in the presence of this additive. Right? So that is the sort of like the structure of the Lindelar catalyst. Right? So this is a general reaction scheme. So if you're running the reaction with the hydrogenation reaction with the Lindelar catalyst, then again you can stop the reaction at the alkene stage. But this is a catalytic hydrogenation reaction on the surface. Reaction has to the syn type, right? So you are getting the syn addition product in this case. That's why you are getting the cis product selectively, not the trans one. Right? So if you want to make the cis alkene from alkyne, then you have to think about this catalytic addition. This is the most effective way, probably. Catalyst deliver hydrogen to one side of the triple bonds, right? Because if you think about the reaction, there's a surface of the catalyst, right? And hydrogen will attach to the surface of the catalyst in alkyne approach, right, to the surface. So it has to occur the one side of the triple bonds, right? And that's why the reaction takes place. The syn type addition will give you a cis product. Right? That's the basic idea. You have a scheme here as well, right? So hydrogen attached to the surface, alkyne approach to the surface, syn fashion, and that's why you're getting the syn addition in the first place. 그래서 기본 아이디어는 간단하죠. 팔라듐 설페이스에서 혹은 플라티늄 설페이스에서 하이드로지네이션이 잘 일어난다는 건 알케인 챕터에서도 배웠어요. 그래서 더블 본드를 알케인으로 리덕션 시킬 때, 하이드로지네이션 시킬 때도 저희가 팔라듐 퍼시, PT 퍼시 이제 그렇게 표기된 촉매를 쓴다고 했죠. 그 PD 퍼시, 그죠? PT 퍼시 이 노테이션의 의미는 팔라듐 메탈 나노 파티클이든, 그죠? 나노 파티클이라고 들어봤을 거예요. 나노 입자, 나노 사이즈 입자, 아니면 마이크론 사이즈의 촉매든, 아니면 조금 더 큰 사이즈의 팔라듐 입자든 상관없어요. 팔라듐 메탈의 아이덴티티를 가지고 있는 어떠한 구조물이 카본 지지체 위에 올라가 있는 어떤 형태의 촉매를 많이 씁니다. 그리고 surface 촉매 혹은 heterogeneous 촉매라고 부르는 이유는 이 PD 퍼시, PT 퍼시는 여러분들이 수소화 시키려고 하는 알카인 대비 엄청나게 큰 구조물이에요. 그래서 보통 솔벤트에 녹지 않습니다. 솔벤트에 녹지 않고 슬러리 타입으로 반응이 가거나 이제 인호모지니어스한 환경에서 반응이 가기 때문에 저희가 헤테로지니어스 촉매 혹은 헤테로지니어스 촉매 환경이라고 이야기를 하는 거예요. 결국에는 서페이스에서 이제 반응이 일어난다라는 이야기고, PD 퍼시, PT 퍼시 이제 서페이스를 좀 줌인을 해서 보면 반응이 일어나는 이제 액티브 사이트를 줌인을 해서 보면 이제 저렇게 모사를 해볼 수 있다라는 이야기이고, 이제 린드라 캐탈리스트는 그럼 뭐냐? 플라티늄이나 팔라듐 서페이스의 에디티브 효과를 좀 더했다라고 이해하시면 돼요. 그래서 레드 아세테이트나 퀴놀린이나 칼슘 카보네이트 등등 다양한 에디티브 효과들은 사실 학계에서는 연구가 많이 되고 있는데 교과서에서는 아주 간단한 하나의 example만 배우는, 대표적인 example를 배운다라고 생각하시면 돼요. 그런 에디티브를 이제 더하면 왜 알카인이 알켄에서 반응이 멈추냐 궁금하잖아요. 근데 기본 원리는 에디티브가 서페이스와 인터랙션을 하는 거고, 에디티브가 서페이스와 인터랙션 하면서 알켄은 선택적으로 이제 서페이스에서 반응성을 잃게 되고, 알카인만 이제 첫 번째 스텝에만 반응하게 일종의 서페이스를 좀 디액티베이션 시키거나 포이즈닝 시키는 효과를 얻을 수 있다. 그렇게 간단하게 이해만 하셔도 될 것 같아요. 그래서 조금 액티비티를 줄인 헤테로지니어스 촉매를 쓴다. 그러면 알카인에서 알켄으로 변화된 이후에 두 번째 스텝이 갈 만큼 액티비티는 없는 거예요. 두 번째 스텝에서 첫 번째 스텝에서 반응이 종료가 된다. Okay. So that was the sin addition, right? If you're running game, the reaction was right, the heterogeneous surface, heterogeneous catalyst, right? And with sort of like deactivated or poison surface, you can stop the reaction at the end of the first step. And because the catalytic hydrogenation reaction will take place in syn type, right? By nature, or in the first place, that's why you're getting the syn addition product. Hydrogen will attach to the surface, and olefin or alkyne has to approach to that surface because the surface is the active site for hydrogenation reaction. And that's why the hydrogen will deliver to only one side of the double bond or triple bond, right? And that's why the reaction is syn type, okay, in the first place. But there's a case you want to make trans, right? Trans-alkene from alkyne, right? And people develop the synthetic condition, the reaction condition, to get this trans product selectively, right? And this is called the dissolving metal reduction, right? So you are basically dissolve this metal, sodium or lithium metal, in liquid ammonia, and this is a good condition for the N-addition, right? N-addition of the hydrogen to alkyne, and that's how, right? That's why you're getting the trans product under this condition. Right? So under this condition, right? If you dissolve metal, sodium or lithium metal in ammonia, right? And this is good environment again for the hydrogen transfer process, right? And for hydrogen transfer, right, you may need the electron and also the proton, right? So proton, one equivalent of proton, right, and electron. If this, right, transfer, then you can get one hydrogen, right? You can formulate one hydrogen, right? And in this condition, right, electron comes from metal, sodium or lithium, and proton comes from the ammonia, right? So metal again serving as an electron donor, and ammonia you're serving as a proton donor. And you expect sort of like stepwise reaction scheme or reaction mechanism, the electron transfer from metal and proton transfer between, right, the mediated ammonia, right? So ET means electron transfer, PT stands for proton transfer. The combination of this will result in the hydrogen transfer in that. Okay? And this is the mechanism, right? It's just not that complicated. You take a look at, right, one step, right? One by one, you can easily rationalize, right? And you can also rationalize why you're getting the transforming product following this step. But before taking a look at, right, you should distinguish, right, this barred, single barred arrow versus double barred arrow, right? The single barred meaning you have this type of, right, arrow, right, compared to the double barred arrow looks different, right? And this is the notation for the movement of the radical electron, right? Not movement of the pair of the electron, right? When the single electron moves, you need to use this, right, single bar notation, right? That's the correct. And here you have sodium, right? Sodium metal, right? And sodium metal has a very low ionization energy, as you know, right? It readily give up the electron. In other words, it tends to give the electrons to the other species around. If our kind is around, right, then this electron will get donated, right? This will deliver to the archive, and following the single bar arrow, you have this is a single bar arrow, right? Indicating the movement of this single electron, okay, not the pair of the electron. And in the triple bond, right, you can identify the movement of the electron, right, one by one. And this will give you this radical anion as intermediate, right? And this is the structure of the radical anion, and you can rationalize why, right? These pair of the electron and this radical, right, tend to occupy, right, in a trans, right, location to mediate the repulsion between, right, electrons. Right? So this is more preferable, right? You can imagine, right, cis version of the geometry, but there is a repulsion between this two, right, electron densities, right, which is not good. So that's why the transform is more preferable after first electron transfer step. Right? So first step was the electron transfer. Okay? The second step is the PT, proton transfer. Right? So you have this anionic location, and you have the proton donor, which is ammonia. Right? And then this anion will take the proton from the ammonia. Okay? Then you can rationalize how this binary, right, radical is formed, right? And then third step is again the ET, the electron transfer. So you would have more sodium metal around, right? The sodium is dissolved in this condition, in this, right, media, reaction media, and this will, right, provide one more electron, and then following this single bar arrow, you can rationalize the movement of this single electron, and this will give you this binary anion, right, intermediate, right? And this is the structure of the binary anion, and you can rationalize why transform is preferable again. Right? If you have cis form, then there's still repulsion in this case between two methyl groups, right? But if you have trans, then there will be no steric repulsion between these two methyl groups. So this one is preferable, right? That's why you have to transform well as well. And the last step is the last PT, right? The proton transfer step. And then again, ammonia is serving as a proton donor, and as a result, you will get the final transfer key. So role reaction scheme will take place: ET, PT, ET, and PT. So electron transfer from sodium metal or lithium metal, and proton transfer from ammonia. So proton donor, in this case ammonia, and electron donor is a metal, sodium metal. So as a result, again, if you run this dissolving metal reduction, you are selectively getting the trans product. 그래서 이 메커니즘을 따르면 왜 트랜스 프로덕트가 생기는지 이제 설명하실 수 있을 겁니다. 그렇죠? 트랜스 프로덕트만 만들어보고 싶다. 여러분들이 유기화학자라고 생각을 해보면 그런 생각할 수 있잖아요. 캐탈리틱 하이드로지네이션을 하면 시스만 만들어지네. 그러면 트랜스만을 만들고 싶으면 어떻게 해야 될까? 이런 궁리를 해볼 수 있잖아요. 여러분 유기화학자라면 그 조건을 이제 찾은 거고요. 옛날에 유기화학자들이 그중에 이제 typical example 또 다양한 반응들이 많이 있습니다. 텍스트북에 나오는 아주 typical한 example, dissolving metal reduction 저희가 배운 거고요. ETPT, ETPT가 sequential하게 일어나는 게 핵심이고 ETPT, ETPT가 일어나게 하기 위해서 필요한 일렉트론 도너, 프로톤 도너가 이제 소듐 메탈, 리튬 메탈이 암모니아에 녹아 있는 형태로 반응 미디어에 공급이 되는 것이고 이 메커니즘을 따르게 되면 ETU에 생성되는 라디칼 애나이온 그리고 ETPT 그다음에 한번 ET가 더 일어난 이후에 생성되는 바이닐릭 애나이온의 시스 vs 트랜스의 안정성을 따져보면 트랜스가 유리하다라는 이야기입니다. 그 결과가 결국 반응 프로덕트의 셀렉티비티 결정짓게 하는 요소가 되는 겁니다. Okay. That was actually pretty much every reaction that we will cover for the alkyne, but this is the last reaction, right? Very important reactions. This will lead to the SN2 type reaction, actually. So alkyne thus far we discussed the addition type reaction, right? But if you have base around, if you're using the terminal alkyne, you can deprotonate that terminal hydrogen to generate the kappa anion, and that can serve as a nucleophile in a different way. That's what we're going to study. And then before getting at, you have to recall the relative electronegativities of the carbon, right? An alkyne, of course, have sp hybridized carbon, right? And you know that sp hybridized carbon is the highest electronegativities. You have highest S character. In this case, you have 50%, right? Not 50% of S character, right? For sp hybridization. For sp2, you have 3%, right? And for sp3, you have 25% S character. Larger the S character, more electronegative. Because you have more S character, right? The distance between the nucleus, right, will get smaller. So you have more, right, the fold type structure, and this will lead to higher electronegativities. Right? As a result, right, the pK trend will follow. Right? These terminal CH bond will be more acidic, right? Most acidic in this series actually, compared to ethene versus ethane, right? This CH bond is most acidic. The pKa of this CH bond is 25, right? Arcane or ethane in this case 40, and for the ethane arcane 60. Right? It's pretty acidic, right? Because of the high S character in this carbon. Right? So after deprotonation, right, getting the proton, in other words, you can expect to have this kappa anion. And if you have higher S character, this minus charge can get stabilized better. Right? This carbon, in this case, is more electronegative. It's a happier scenario, relatively speaking, compared to, right, this case versus this case. Right? That's why the CH bond is more acidic in the first place. Right? You need to think about the the stability of the conjugate base, right? As we learned in chapter 2. And this is the relative acid strengths, and you can find the alkyne in the middle. It's pretty acidic, right? This OC1 is more acidic than ammonia, less acidic than water. So if you have a proper base, right, then you can deprotonate this OC1 to make this carbon anion, right? And the typical reason you can use is the amide ion, right? The anion, NH2 minus, and this can easily, right, deprotonate these CH bonds, right? As a result, you will get, right, the ammonia and also the carbon anion, in this case, acetylide anion. So you have minus charging, right? And again, because of the higher S character on this carbon, right, this base, this conjugate base is actually quite stable, right? That's why this is a weaker base. So from strong acid and strong base, you are getting weaker base and weaker acid, right? That's always the case, right? The equilibrium for acid-base chemistry, right? And then for that, right, you need to actually be strong enough base, and you have here the amide anion, which is good enough, strong enough, right, for this reaction to take place or make the equilibrium the right hand side. In other words, reaction going forward. Right? But if you're running the reaction with the hydroxide anion, the basicity of hydroxide anion is insufficient, so you cannot make equilibrium go forward. Right? So you need the amide ion, NH2 minus. And if NH2 minus around, you can generate this carbon anion from the terminal alkyne, and this can, right, participate in the alkylation reaction. We'll learn the mechanism for this in a different chapter, actually, in SN2. When you learn about SN2 reaction, you learn about the detailed mechanism of this a lot. But for now, you can accept this, right, reactivities. You have carbon anion, and this can attack this electrophilic carbon and bromide can liberate. As a result, you are generating the bond between these two carbons. So you can formulate a new carbon-to-carbon bond. The carbon here and carbon there. This can be attached. And this is called the alkylation reaction because you are putting the alkyl group. Okay? So this is another scheme. Again, from the terminal alkyne, after deprotonation, you can generate this carbon anion, and this can attack. Right? This can serve as a nucleophile. Right? Nucleophile can serve, right? Can participate in this substitution reaction, SN2 type substitution reaction. But for now, right, you can think about this as simply the alkylation reaction. Right? And following the arrow, you rationalize how this product is formulated. Right? It's a quite useful reaction. You want to increase the number of chain, right? The hydrocarbon chain. You can think about this reaction. So as a result, you can think about this overall scheme for two-step reaction, starting from this terminal alkyne. You can deprotonate using this strong base, the amide anion. This will deprotonate, right, the terminal CH bonds to generate this acetylide anion, the carbon anion. And this can serve as a nucleophile for the alkylation step to give you the final product. Okay? So knowing all about this, and knowing the addition type reaction that we just discussed before, perhaps you can propose the synthetic pathway, right? Starting from this substrate, you should be able to synthesize, right, this product. Right? So how can this compound prepared or synthesized from this terminal? 그래서 이제 유기화학을 공부를 많이 하시고 나면 여러분들이 하실 줄 알아야 되는 게 이런 거겠죠, 그죠? 반응을 충분히 익히시고 나면 이제 프로덕트가 하나가 주어졌다, 스타팅 머티리얼이 주어졌다. 그러면 스타팅 머티리얼로부터 이 프로덕트 어떻게 합성할 건지, 반응 경로를 이제 짜실 줄 알아야 돼요. 그러니까 뭐 역설계하는 거죠. 프로덕트가 이게 나오기 전 스텝이 뭐가 필요하고 그거의 전 스텝은 뭐가 필요할 건지를 조금 짜임새 있게 생각을 해보시면 이제 계획을 하실 수가 있겠죠. 실제로 유기화학이 내가 좋다. 나는 이제 합성도 배워보고 싶다. 그러면은 뭐 이제 하실 수 있죠. 이런 지식들이 좀 누적되면 복잡한 프로덕트도 설계를 하실 수가 있습니다. 나중에 지식이 축적이 되면 그러면 이제 여러분들이 정말 복잡하게 생긴 내추럴 컴파운드들도 다 합성을 하실 수가 있게 됩니다. 그래서 한번 뭐 잠깐 고민을 해보실래요? 터미널 알카인으로부터 키톤을 만들어야 지금 그러면은 우리 키톤 생기는 반응 앞에서 많이 봤잖아요, 그죠? 슬라이드 뒤에다 답이 있어서. Okay, so again, after learning all the reactions, right? The key reactions, you should be able to design the synthetic pathway, right? Given product, right, and substrate, how can you, right, make this one? Right? And this is perhaps the right answer. Right? So you can start from 1 butene actually, right? And from 1 butene, and after deprotonation and alkylation, you can make 3 hexene. And from 3 hexene, you can add water, which will give you, right, this phenol, and tautomerization will give you the product that you want. Right? So you can maybe think about the backward, right, from the product, right? In order to make this ketone, right, you should think about enol, right? You know about the keto-enol tautomerization. And this enol can be formulated from this internal alkyne, if you know about, right, the addition of water. And then you can think about then how can you make this from this, right, the starting material. And since you know the alkylation reaction, you can propose the following reaction: deprotonation and alkylation, the SN2 type reaction of this alkylobromide. Okay. You can make this, and addition of water, tautomerization will give you the target product that you want. Okay. So alkylation first again, right? And enol addition, water addition to generate enol, and tautomerization will give you the product. Okay, we need ones, but maybe you can think about, right? The target product is this, the aldehyde, right? And starting from this, right? How can you make this? Right? That was the original question. Right? And then again, you can do the retrosynthetic analysis, which means you should go the reverse direction one by one. Right? So starting from the final product, you can imagine the step just before. Right? And because this is a aldehyde, perhaps you can think about this type of olefin, if you recall the ogenolysis. Right? Then you can generate, right, this olefin, from this olefin to this aldehyde. Right? And to make this olefin double bond, you can think about alkyne, and you can stop the reaction after first addition of hydrogen using linear catalyst. You can make that. Right? And of course this, right, can also make from this terminal alkyne in the presence of base and alkylation, right, you can generate this internal alkyne with increased number of carbons, right? So that's sort of like the retrosynthetic analysis you can imagine. And the bottom is the normal synthetic sequence, right? Starting from this, right, terminal alkyne, deprotonation, alkylation will give you this internal alkyne with increased number of carbon, and linear catalyst hydrogenation reaction, right? Using linear catalyst can be used to stop the hydrogenation reaction, and the alkene and ogenolysis, right, will give you this oxidative cleavage product, right? The aldehyde. So that's one possible answer. What about this? How can you make this 2-bromopentane from the ethane? Right? The simplest possible alkyne. So you can do the retrosynthetic analysis again. So from this target product, you can think about what kind of substrate can give you this product. Right? And then you can think about maybe the HBr addition, HX addition to the alkene. Right? So if you have alkene around here and using the HX for HBr as addition reaction, then protonation will take place at the terminal position first to give you a secondary carbocation and halide tag. Right? The bromide tag will give you the following product. Right? Then you can think about how can you make this olefin more double bond from perhaps the alkyne. If you use the Lindlar catalyst, the hydrogenation reaction, using Lindlar catalyst, you can stop the reduction at alkane stage. Right? And of course, this can be made from the deprotonation and alkylation from this given starting material. Right? So that's the retrosynthetic analysis. And for the normal interaction, again, from this substrate, deprotonation, alkylation will give you this alkyne, still the terminal alkyne, but the more carbon chain. And hydrogenation using Lindlar catalyst will give you selectively the double bond, the olefin, the alkene, and the HX addition, HBr addition will give you the secondary bromide. Okay. What about this one? 2,6-dimethylheptane. You want to make this from these two type of substrate, right? From the terminal alkyne and argyl bromide. That's what you should use for making this product, 2,6-dimethylheptane. Right? Then you can do retrosynthetic analysis again, right? So from this structure, the alkane, maybe you can think of the alkyne, right? And if you're using the catalytic hydrogenation reaction condition without the activation, without poisoning, just normal catalytic hydrogenation reaction can give you this alkane from the triple bond from the alkyne, right? And this alkyne, this internal alkyne can be synthesized from two options actually. This can be made from the left-hand side, if you are using the base in this argyl bromide, then you can imagine the alkylation can take place to formulate the bond between this carbon and this carbon. Right? Or you can think about the bond formation between this carbon and this carbon as well. Right? So for this part, you can use this terminal alkyne, you deprotonate, then you can generate this carbon anion as tellite anion, and this can participate in an alkylation reaction to generate the bond between these two carbons. But we'll learn about this later. The secondary halide is not good substrate for the alkylation reaction or SN2 type reaction. That's why you have to choose this way. So starting from this alkyne, deprotonation, alkylation, this is still the primary halide, which is good for the alkylation reaction, SN2 type reaction. And after forming the bond between this carbon and this carbon from this first step, and then followed by the catalytic hydrogenation, full reduction of the triple bonds will give you the target product that you want. Okay. I guess this is the final one. Yeah, what about this one? This is actually a simple one. You can make alcohol, from this terminal alkyne. And you can think of perhaps the hydroboration, from alkene, So for making this, you can first think about alkene, and after right? Hydroboration followed by oxidation. You can create the arc rotor at the terminal position, right? And of course, for this olefin, you can use the Lindlar catalyst, the catalytic hydrogenation reaction. So from this alkyne, hydrogenation using Lindlar catalyst can stop the reaction at the alkene stage, right? Because in this case, cis or trans doesn't matter. You can also think about maybe the dissolving metal reduction that we studied too, right? Doesn't matter cis or trans. And hydroboration will give you, right, the terminal boron substituted, right, alkene in this case, right, because you were running the reaction at the olefin double bond, and oxidation will give you the terminal alcohol, right, the primary alcohol in other words. What about this one? You want to make E, right, the stereoisomer, right, E2-pentene, right? So you need to make this one selectively, right? And you can do again the retrosynthetic analysis to make this one. You can think about alkyne, and if you run the reaction, right, using dissolving metal reduction condition, you can perhaps get, right, the trans products selectively. Okay? And to make this alkyne to an alkyne course, you can think about again the deprotonation and alkylation sequence. So deprotonation and alkylation sequence will give you this alkyne, and after, right, one more, right, alkylation will give you the internal alkyne that you want, and dissolving metal reduction will give you the trans alkene selective. Okay? So starting from this, right, simple substrate, and you can design, you can make the product. Right? What about epoxide, right? You want to make the epoxide, the oxygen and orange, right? And you have to make this cis 2,3 diethyl oxygen. So you want to make this very selectively. Again, starting from this alkyne, the simplest possible alkyne. And you know about the peroxy acid addition reaction that you already studied in alkene chapter. To make this one, you can think about this alkene, this olefin, and if you run, right, the epoxidation or peroxy acid addition, you can put, right, the oxygen, right, in the middle to make this epoxide. And to make this double bond, the olefin, of course, you can think about alkyne, and you can think of then syn type addition to make cis product, right? And you have to stop the reaction at the alkene stage. That's why we're using the Lindlar catalyst, right? And to make this triple bond, of course, you can think about the alkylation. So starting from this, again, the substrate, deprotonation, alkylation will give you this alkyne, and one more alkylation will give you the internal alkyne that you want, and hydrogenation using Lindlar catalyst will give you the cis double bond containing species, right? The alkene selectively, and then peroxy acid addition like MCPBA can be used, right, to make this epoxide. Okay. I guess this is really. 네, 그래서 지금 시간이 다 돼서 여기까지 하고요. 지금 나머지 2개 이젠플이 있는데 한번 연습을 해보십시오. 그거 저랑 간단하게 커버하고 리뷰를 좀 충분히 해보시면 되게 익숙해질 거예요. 다음 시간에 저랑 마지막 2개 다뤄보고 그리고 다음 챕터로 넘어가도록 하겠습니다. 예, 수고하셨습니다.